sit here, so you don't have a 3-inch.
Another one, or you just readjust whatever you have?
No, you need another one, which you don't currently have, but you could order it and we'd send it out to you. Yeah, we'd send you the whole assembly, and then you could just bolt it in. It's only 2 screws to attach it, and I'll talk you through that probably. We're going to have about an hour left today, so we can carry on doing some hardware and configuration things where I can show you things like wafer clamp setup and platen leveling, this kind of thing. I'll be able to demonstrate all that to you. Yeah, for about an hour this afternoon, and we have to cover the rest of it tomorrow. And also tomorrow we may be able to do some bonding with some of your wafers. Do some tests while I'm still here if we've got time. Yeah, the first thing I need to do is run through the rest of my training sort of schedule with you, and if there's time left over, we can do some bonding with your wafers.
Is it like a Ethernet port from the backside?
There's an Ethernet port on the back of the PC, yes. Yeah.
How does from the backside of the machine, or
You would have to take this panel off, and then you can slide the PC forward and gain access to the back of it. There's a strap, a metal strap inside there as well that secures the PC down, so you have to loosen that off first as well. And the screws for that, I'm not sure if they are accessible from the top or from the bottom. If they're accessible from the bottom, you also have to remove this front panel to get underneath. So it's one of these classic things, you want to do something simple like plug in an Ethernet cable, you've got to take half the machine apart first and then plug it in.
I wish we already had some silicon perforated wafer and glass wafer to try. Like a perforated silicon wafer and the glass. But that perforated silicon wafer needs to be like, but it needs to be, I think, full wafer also.
you cannot do wafers. You will not be able to hold the vacuum. So if you have full wafers, like what's the point?
It is not full compact.
So you have to have like cavities in circle, and then you do this bonding in vacuum. Then you reflow the glass to fill those. And then you do like
I mean, you just heat it after you want.
yeah, you put it in a furnace or something. Because there's like I have some wafers. I have one wafer.
Okay, sorry to interrupt, but the 10 minutes is finished, so now I'm just going to control force, bring the wafers into contact with the plasma still there.
Is it possible to see like with the IR, like see the like one wafer, and then when the bond forms, you can see anything?
Are you applying
Yeah.
force right now?
No, I'm not. It's still separated, so
So you do the control separate there.
I'm doing controlled force now, but obviously it has to bring the wafers into contact before it can control the force. So it's just closing up the separation. Yeah, I think we can do that. I think you're right. We can. Okay. If I had double-side polished wafers, I would be able to do that. As I only have single-side polished wafers, I can't do that because it scatters all the light and I can't see through it. But you're right. If we had double-side polished wafers, you would be able to use the IR to watch the bond wave propagate, but only over a small hole's worth. You can't watch it propagate over the whole wafer. Let's just try, give it maximum power. Yeah, maximum power, I still can't see anything, so sorry, no.
Actually, this one I did, but okay, I can sacrifice.
Okay, to speed this up a bit, when you're in manual control, it moves faster so than when it's under force control. So I'm just going to bring the wafers into sort of some form of near proximity quickly, and then we'll go back to using force control because it's taking forever.
Probably if you have
Huh?
if you have the manual, it would be.
This is quick, yeah. But then, if you have the manual system, you have to sit there and monitor the force yourself and adjust it little bit by little bit all the time. So, like when you make contact with an anodic bond and it's hot, or if you make contact and then start heating, there's some expansion, so the force rises. You've got to sit there and turn the wheel a little bit, turn a little bit. So you have to do the force control, which is boring. That's a disadvantage of the wheel. And also, if you want to apply 25 kilonewtons, you have to be pretty strong to turn the wheel to gain enough force on it. Right, there we have it. We're in contact. Start the 5-minute timer. I think basically already the bond will be done, but we'll give it 5 minutes for,
How do you know we are in contact?
because we have 500 newtons of force being applied.
Okay.
So we are in contact and we have a clamping force between the wafers. Turn the plasma off. What we can now do, we can turn the pressure control off. Just allow it to pump out. I think this webcam has crashed because there's no plasma anymore and it's still showing it there, so that image has crashed. Yeah, that's about it.
Can we close the valve? The insulation valve? Or it doesn't matter?
Yeah, you can close it, but no, but let's leave it pumping out for now. So we've got a safe kind of vacuum environment there while the bond's forming.
So basically, you're still applying force, but you're already removing the pressure, the vacuum.
So what I'm doing now is I'm basically pumping out any products of the plasma. So now there's just should be sort of a safe vacuum inside the chamber. So I think the bond will have already formed, but the AML process says that I have to use 5 minutes. I have to wait for 5 minutes, which strictly speaking is unnecessary because a direct bond wave is going to form in seconds. That failed to start, so I think we'll wait for 3 minutes. We've done basically 2 minutes already. So I make no guarantees as to whether this bond will have worked, but hopefully it should be at least stuck with some Van der Waals interaction, so it's a weak bond. And then you can anneal it in a furnace. Or you can do annealing in situ up to 500 degrees, but with controlled heating. This is the only application I know of using this controlled heating. So we heat at 1 degree per minute up to 100 degrees. But that takes an hour and 40 minutes, so I don't want to bother doing it now. It's easy.
Theoretically, we can do it inside here without having to.
Yeah, but you can only do it to a maximum of 560 degrees, which for an activated bond is probably enough. For a non-activated bond, you want to do the annealing at say 1,000 degrees in a furnace.
We do it at 400 for 8 hours.
Is that what you do? So you could do that in situ, do it overnight kind of thing. Yeah. Annealing.
Plus one bonding.
Why do you need to
Chemical bonding.
Okay, I've had enough of this, so I'm gonna stop now. Release the clamp. Separate. And then we can vent her up.
You don't need to do annealing for working
For a no-dick, no.
after.
It's already a very high strength bond. There's simply no point. Right, let's take this out and see what we have.
What are you guys going to be making? Just sensors or?
Yeah. I think you're making.
We have big holes in this tool for too many processes.
A lot of products.
Different type of things.
Still a little bit warm, so cool down.
What's the explanation for this? So the direct one,
Yep.
how it happens for another bonding, we know, like dioxide bonds with silicon. How this
Process?
So yeah, I think we have at least a sort of Van der Waals bond, and that has kind of worked. If you put that in your furnace and try to anneal it, it would probably fall apart, but you can try.
Okay.
If you anneal it successfully and it doesn't fall apart, I'll be quite impressed. I'll be quite happy with that. Okay, so the way direct bonding works is you have a hydrated wafer surface. So there's essentially hydroxyl groups kind of dangling bonds on the wafer surface. You're going to bring those into contact. So initially we have kind of surface tension interaction, which is what we've got there. When you bake it out, a chemical reaction happens. It will generate a siloxane bond. So where's some paper? We have the wafer surfaces. That's going to bond to that, and you're going to generate hydrogen as a byproduct. So obviously for every 2 bonds that forms, you're going to get 1 mole of hydrogen come out. So it's going to give you a bond like that, another siloxane bond, evolve plus hydrogen.
So this bond will only happen after annealing.
Yes, exactly. So this reaction is only going to happen during annealing, which is why it's going to generate hydrogen gas. So if we've used water injection, we're going to have a lot of moisture on the surface, and we're going to generate quite a lot of gas. So if you have a textured wafer with escape paths for that gas, it'll be fine. If you don't have any escape paths for it, it basically is going to create bubbles, and you'll have voids in the bond. So hence, it's all a trade-off between bond strength and voids. I think there's.
Is this cool for like pure silica wafers with the same chemistry
For silica.
silica?
Yeah, I think it would be similar chemistry, yeah.
So the OH part is what generates the bond.
Yeah.
So in theory, for example, if someone wants to do the heating here, like we asked for 4 hours for 400 degrees, right? So how is it going to happen? Like you first make a contact, and at which moment do you heat, like while still in contact, or you?
Sorry, are you referring to if we do annealing in situ?
Yeah.
Yes, you'd leave the wafers in contact and you do
Just anneal it and
the annealing, yeah. So what I would recommend is that you take it up from room temperature to 100 degrees at a controlled rate of 1 degree per minute, because that's up to 100 degrees is when the majority of your hydrogen is going to form. So if you're heating it slowly, it gives the hydrogen time to escape, and it's going to minimize void formation. If you just wang it straight up to high temperature, uncontrolled, the hydrogen doesn't have any time to escape, it doesn't really have anywhere to go. So the process that our process engineer has come up with and that he uses, he would do room temperature to 100 at 1 degree per minute, 100 to 200 at 4 degrees per minute, and then maximum heating rate to whatever your ultimate annealing temperature is. So in your case, full speed from 200 to 400, and then dwell for your annealing time of 4 hours. So in total, that process would take you an hour and 40 minutes, another 120 minutes. Yeah, probably take you about 6 hours to do that, to do his method with combine your 2 methods if you like.
We do room temperature annealing for 4 days. We just keep it in room temperature.
Really?
Yeah. We have cavities, and then if we just anneal it, the cavities will expand and then open up and open.
Ah. I don't understand how annealing is going to work at room temperature. It needs the energy, it needs the heat to actually overcome the activation barrier to get that chemistry to happen. So I don't quite see how your annealing is working at room temperature.
I think it's just to barely somehow remove the hydrogen maybe, and then we do a high temperature with less than 1 degree per minute.
I mean, in theory, if you have a really sort of thoroughly activated surface, there's a chance that you may have some slow reactions happening at room temperature, and over 4 days, perhaps maybe you get some bonds forming, but I think that would probably still be quite a weak bond after that time. And you need some energy, some heat to overcome the act. As far as I know, this plasma ring, it reduces the activation barrier, so it reduces the annealing temperature from 1,000 down to sort of hundreds of degrees. As far as I know, it's not efficient enough to do room temperature direct bonding. I know room temperature direct bonding is kind of the holy grail of the bonding world, and I don't believe we've cracked it yet, and I don't believe any of our competitors, I don't believe anyone else has either. It's kind of a dream for everyone that they want this to happen. So, yeah, maybe you'll get a sort of a weakish bond by just leaving it over a few days.
If you do it for vacuum, you can
Yeah.
furnace, and it doesn't debond.
It doesn't debond.
After, we do expansion of those cavities, so we don't want to debond from the bonding surface.
Okay, so you're allowing some gas to escape first for 4 days, and then you put it in the furnace, right?
For annealing, yes.
Right, okay, yeah. So the furnace is what's doing the annealing. Leaving it for 4 days, what's that going to do?
So what we do is we rinse with DI water. We just the surface is completely rinsed with DI water. Then we dry and then we bond.
Right,
After activation.
yeah.
After activation, we just again rinse with water. So we have a lot of probably surface bonds or
Yeah, so you have some, yeah, you'd have your surface tension interactions happening there. So I guess your 4